Talked about elements being things only made of what? One kind of atom. And how there's 100 and something elements on Earth today. Then we made a list of elements that are important to life. And like I said, eventually this thing's going to work. And I gave you that acronym. I said make sure you know the acronym. CHNOPS, CHNOPS. And that was carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Said those are the most important ones for living things, by far. We mentioned some other ones that are kind of important. Like, for example, what's Fe? Iron. We mentioned calcium. We mentioned sodium. We mentioned potassium. All important for living things. We did spend some time talking about molecules. And we said a molecule is a group of atoms that are what? Bonded together, stuck together. We spent a lot of time yesterday talking about different kinds of bonds, and then we're going to focus on that here for just a minute. Samantha, join us, please. Covalent bonds. We said are bonds that happen between metals that are, between atoms that are non-metals. Where in that periodic table are the non-metals? Right side, right? On the other side, that little line between aluminum and silicon and germanium and arsenic. Everything to the right of that line, non-metal. When things make covalent bonds, what are they doing with their electrons? When things make a covalent bond, what's happening with electrons?
They're either giving it or they're giving it out.
No, they're not giving, they're what? They're not getting, they're sharing. Remember I told you it's kind of like communism. Covalent bonds are like communism. Share everything. They're sharing until they get to what magic number? 8 of what electrons? What kind of electrons? The valence, the ones on the outside. Nice. 8 electrons till you get to the 8 valence. So we did an example. Let's put another one up here for a second. Let's say that we were talking about oxygen gas. What's the oxygen that you're breathing? What's the formula for it? O2. O2, right? So let's take 2 oxygen atoms. Oxygen's a non-metal, right? How many valence electrons does oxygen have around it? It's in column 6A, right? Look at the green numbers. Bi 6. It's got 6. Each one of these oxygens has 6. They're non-metals. They're going to form covalent bonds. All right, now here's the deal. They're going to share. First thing you do is you share one from each. So let's take one from here. Let's take one from here. And let's draw those shared ones in the middle. Okay. Right now, how many electrons, valence electrons, does each oxygen have? If it's using 2, 4, 5, 6, 7. This one has 2, 4, 5, 6, 7. Are these oxygen atoms good to go? No. So if you share one pair and that doesn't work, what do they do next? They share another pair. So we take another one from over here and another one from over here, one from each side. Draw those in the middle. So now this oxygen is using 2, 4, 6, 8. And this one's got 2, 4, 6, 8. And we call that what kind of bond? That's called a double bond because they're sharing what? 2 pairs. That's an oxygen gas, O2. It's a covalent bond. Sharing electrons, sharing valence electrons to get to 8. Remember that things with covalent bonds have no overall charge because the number of protons is equal to what? Number of electrons. But there can be covalently bonded things that are polar, which means that one side might be what? Positive and the other side might be negative. But overall it's still what? Still neutral. What's the most famous polar molecule? Water. And what that causes to happen is when 2 waters get next to each other, what do? They stick together. And what's that sticky force that holds them together called? It's called a hydrogen bond. Hydrogen bonds hold polar things together. They act sort of like glue. And those hydrogen bonds give water a lot of the properties that they have. The other kind of bond we talked about was ionic. What's an ion? Ion is an atom that is what? Charged. To become charged if you're an atom, what do you have to do? Gain or lose something. You have to gain or lose electrons. To become positive, which of those do you do? Are you gaining or losing to become positive? Losing. If you give away negatives, electrons are negative, right? If you give away negatives, you become more what? Positive. But, on the other hand, if you gain negatives, you become more what? Negative. So, gaining electrons makes you be a negative ion. Losing electrons makes you be a positive ion. Regardless, let's look at an example. Ionic bonds tend to happen between metals and nonmetals. A metal sticking to a nonmetal. For example, let's say we took potassium. What's the symbol for potassium? Okay. How many valence electrons does potassium have? One. It's in column 1, right? It's got one valence electron. Draw that dot there. And let's say we're connecting that up to, say, bromine, which is element number 35, Br. How many valence electrons does the bromine have? Try again. 7. It's in column 7, Bii, right? This thing, to get to stable, needs to gain an electron, right? What does the potassium need to do to get to stable? Give away one, right? To drop down to that next level that already has what in it? 8. So what happens is this electron moves over here. Well, potassium just lost an electron. So now it's what? Charged. Plus 1. You lost a negative, it becomes plus 1. Bromine gained an electron, so now it's what? Minus 1. And what holds these two things together now? Why are they now stuck? Positive attracts negative, right? That's what an ionic bond is. It's positive attracting negative. Things that have ionic bonds are called salts. So that's a salt, KBr, just like NaCl is a salt. And which kind of bond do we say was stronger? Ionic or covalent? Ionic. These are hard to break. It's hard to melt, hard to break apart at all. Hey, Michael, let's put that up, please, sir. All right, we did spend some time talking about water. And this water stuff's important. Water is the most important chemical in the universe, at least on Earth. We said 70% of your body's water. We spent a lot of time talking about some properties of water. It's the universal solvent. What does that mean?
Just about anything dissolves.
Yeah, it'll dissolve just about anything. We said that was really important because your blood is what? It's mostly water. And for your blood to be able to do what your blood does, which is carry things around, what do those things have to do? They have to dissolve in it. Oxygen has to be able to dissolve in it. Nutrients have to dissolve in it. Carbon dioxide has to dissolve in it. So water is really, really important to life because it's such a good solvent. It can dissolve things and then move them around. We also talked about this one right here, that water has a high specific heat or heat capacity. And that means it's really hard to what? What does that high specific heat mean? It's really hard to do what to water? Change its what? Change its temperature. You have to add a lot of heat to water or take a lot away to change its temperature. And that's awesome for you because your body's mostly water, which means you could go outside on a really cold day, but what still happens? Your body temperature stays pretty constant. You could go outside on a really hot day. Your body temperature stays pretty constant because water's acting like a coolant inside your body. That's important. We talked too about how water expands as it freezes, which is unusual, which means ice what? Ice floats. And we said that's important because once the top of a pond freezes, what happens underneath that ice? It keeps it liquid and it keeps it warmer. It acts like kind of like a blanket. And that protects the life underneath the top of that body of water. It's going to be very difficult for you to find a lake that's frozen all the way through because of this. Yeah.
What happens if there's like a hole in the ice?
It'll eventually just freeze back over. You're talking like if you went ice fishing or something and you busted a hole in it? This will freeze back over.
Like what the fish died.
No, because the top of the water will freeze back over there, and then it'll go back to being like a blanket again. Clay, what you got?
Are these questions 6 points apiece?
There's 20 of them. 5 points. No, they're all 5 apiece. I'll fix it. They're 5 apiece. All right, let's mention cohesion and adhesion real quick. Cohesion is when what happens? Something sticks to itself, like water sticking to water. And we said water sticks to water because water is what? Polar, charged. And we said adhesion is when something sticks to something besides itself, like water sticking to glass. Why does water stick to glass? Water's polar, and so is glass. Polar things go together. Polar goes together. Glass has a slight electrical charge to it. On the other hand, I talked to you yesterday about those rags I bought at Walmart or Kmart, how the thing. You couldn't get them wet, wherever it was. And what kind of rags did I say they were? Rags to pick up oil. Oil is not polar. So if you want a rag to pick up oil, you need a rag that's also what? Not polar. When you stick that in water, what happens? Polar and non-polar, what do they do to each other? They repel. That's why when you pour like oil into water, what happens? It floats. Okay, it floats up to the top. They don't mix. Yeah.
So a solid object can't be non-polar.
No, it can be. It can be. Just depends on what's going on in the molecules that make it up.
Like how?
Like that rag, like I said, it's non-polar. Very possible. Very possible.
How is glass not polar?
How is it?
Or how is it polar?
It just has to do, it attracts water, in some cases at least, so it is polar. Just depends on what molecules are in it, what it's made out of. All right, let's see. The other thing we talked about in terms of new stuff yesterday were acids and bases. Which one is water? Yeah, but we said yesterday it's both acid and base at the same time, because in a glass of water or in an ocean of water, whatever you're thinking about, a few of the water molecules are doing it this. Whoops. A few of the water molecules break apart, and they break apart into hydrogen, H plus ions, and hydroxide ions, OH minus. And we said that what kinds of things usually give off H pluses? Acids. And what kinds of things give off OH minuses? Bases. Well, water does both. So it is both. But because the amount of this that it gives off is the same as the amount of this that it gives off, what does that mean about its pH? It's neutral. But let's talk a little bit about the pH scale for a second. We said pH runs from what to what? 0 to 14. Things that have a pH of 7 are said to be neutral because this is equal to this, right? H plus is equal to OH minus. But if you go, pH is lower than 7, what can we say about H plus compared to OH minus in the container that's happening in? Well, first of all, are these acids or bases up here? These are acids. What makes it be acidic inside the container is that H plus, there's more H plus in there than there is OH minus. Those are acids. The closer you get to 0, what happens to the acid? Stronger it is. The closer you get to 0, the stronger the acid, which means the more H plus there is inside there. The more you go away from 7, the more you go toward 14, the more basic it becomes. These are your bases. Down here in these solutions, there's more OH minus than there is H plus. One thing that we didn't talk about yesterday, what happens when you mix an acid and a base?
You get something 7.
Let's put a little equation up here. That's called neutralization, when you add an acid and a base together. Now, you never want to try this, but theoretically, here's something you could do. Nobody would ever want to try this. But theoretically, you could take really strong hydrochloric acid. Really strong hydrochloric acid, HCl, right? So strong that if you put like a nail in it, it would dissolve really fast. Really strong HCl. And you could combine that with NaOH, which is sodium hydroxide. That's a base. Again, that's just as dangerous, probably more dangerous than HCl too. It'll cause burns, it can cause blindness if it gets in your eyes. Crazy strong stuff. If they're equal strengths, and you add equal amounts of them together, what ends up happening is this. The things in the front, the sodium and the hydrogen, switch places. So the Na ends up with a Cl, and the H ends up with an OH. So you end up with NaCl, which is what?
Chlorine.
What is NaCl?
Sodium chloride.
That's salt, right? That's sodium chloride. That's the stuff you eat at home. And what's H with OH?
What?
That's water, H2O. Okay? So that's a neutralization reaction. When you add an acid and a base together, they neutralize each other, and you end up with just salt and water. That's a neutralization reaction. So literally, if you were really brave, you could take a small sip of that. Right? You don't want to drink much salt water, but you can take a small sip. And this would be, what would the pH of this be, assuming that those two were equal? 7. It'd be neutral. Wouldn't be dangerous. You wouldn't want to do that, but because it turns out just a drop or two extra of one of these could make this still be really acidic or really basic and really dangerous. Yeah.
If you ever decide they never simplify the fraction, they 0.2 from 5.
Just do it. It's okay. All right. Last thing on this stuff, and then we'll get to the main thing that we want to deal with today. Remember the pHs. Certain things that we deal with on a daily basis are a little bit acidic. Stomach acid's very acidic. It's got a pH of 1 or 2. Lemon juice, pretty acidic. Coke, pretty acidic, pH of 3. Vinegar. Tomatoes and tomato juice, pretty acidic. Coffee's a little acidic, not so much. Rainwater, a little bit acidic. Urine's even a tiny bit acidic, pH of 6. But things like tears, pure water, they're at 7. They're neutral. Your blood is slightly basic. We said yesterday that the blood is usually like 7.35, so just barely basic. And then things like cleaners. A lot of the cleaners that you use in your kitchen or your bathroom at home, a little bit basic. Like, for example, oven cleaners, pH of 13. And there's that sodium hydroxide stuff we were talking about a minute ago, pH of 14. So if you took something, like I said before, something with the lowest pH and something with the highest pH, and you added exactly equal amounts together, you would get what? You would get neutral, and you would get salty water, essentially, right? Hopefully, if you add exactly equal amounts, you would get salty water, pH 7. All right, I'm going to stop with that there. We got to switch gears here for a minute, though. All right, we mentioned yesterday, kind of at the end, that the other thing that we had to talk about before we take this first test is what's called organic chemistry. And we talked about how the organic means it's got what in it? What does organic mean is in the chemical? What does the word organic mean? Carbon. So here's what you need to write down some notes. Organic means it's got carbon in it. It's a carbon-based chemical. Now, there's 120 something elements. But no matter what kind of living thing we're talking about, if we take the water out of them, most of what's left is what? Carbon. In every living thing, whether we're talking about bacteria, fungus, protist, plant, or you. So carbon's pretty special. Most of the chemicals in you, other than the water, are carbon-based. The gas that you burn in your car is carbon-based. The food that you eat is carbon-based. Your DNA is carbon-based. Your proteins are carbon-based. Sugars are carbon-based. Fats are carbon-based. They're really, really important. So there's some things about carbon that you need to know. First of all, know that organic means contains carbon, made of carbon. The reason carbon's so important, the reason it's so good, talked a little bit about this yesterday, is carbon's in column 4 in the periodic table. Okay, IV, right? Carbon's number 6. Means it's got 4 valence electrons, which means at any time it can connect up to how many other things? 4 other things. And that makes it really valuable because what that means is it can build things with lots of different ways. If you got a piece that you can connect up to 4 other pieces, what can you do with that thing? You can make stuff in a lot of different shapes with it. And in biology and in chemistry, shape determines what? What does the shape of a chemical determine about the chemical? What it can do. Shape determines function. So because carbon can build things in so many shapes, it can make chemicals with all kinds of different functions. That's important. Some other things that are important about carbon. On Earth, it's abundant. It's not the most abundant thing on Earth, but it's really, really, there's a lot of it. Let's just put it that way. If you were designing life, you would want to build life out of something there's a lot of, right? There's a lot of carbon. Makes sense. It's kind of small, which means when it makes bonds, they're really strong. Again, if you were designing life, you would want to build it out of something that's hard to break, right? Makes sense. So that's carbon. Organic chemistry is the chemistry of carbon. There's a whole branch of it. And what we want to look at now, and how we'll kind of end our little unit before our test, we're going to talk about 4 groups of what are called biochemicals. You've heard of these before, I'm sure. Carbohydrates, lipids, proteins, and nucleic acids. And we're going to spend not a lot of time, but most of the rest of our time today talking about these 4 little things. These are the 4 biochemicals, or sometimes you'll hear them called biological macromolecules. Now that sounds pretty complicated. What's macro mean though? What's macro mean?
Small.
Try again. Big. Okay. So it means they're big molecules. Micro means small, right? Macro means big. So big molecules, important in biology. Biological macromolecules. So we got 4 groups. Let's start off by talking about the first one here. Let's talk about carbohydrates. Why do you think they're called carbohydrates?
Is it made of carbon?
They're made of carbon and
Hydrogen.
hydrate. What's hydrate mean?
Water.
Water. So they're made of like carbon and hydrogen and oxygen. Carbohydrates.
Foods.
Here's the thing. Carbohydrates are known to most people as sugars. That's what carbohydrates are. They're sugars. Carbohydrates are sugars. Now in biology, sugars have different functions. The most common function of carbohydrates in nature is for energy, what we call quick energy. When you eat sugar, what can you do to it really fast? You can burn it. You can do cell respiration on it, which means you can get energy out of it. You can use it to make what really fast?
Food.
ATP. Somebody's been listening.
Also known as like.
You can use sugar to make ATP really, really fast. That's why we call it quick energy. But another thing that sugars get used for in biology is for structural materials.
Ooh.
Think about this for a second. A tree is mostly made out of what? Wood, which is mostly made out of sugar. A tree is mostly built out of sugar. When you step on a bug, you hear that crunch, right? What are you crushing when you step on that bug?
The exoskeleton.
The exoskeleton, which is made mostly out of what? A sugar, okay? A carbohydrate. So that's what I mean by structural materials. There are lots of things in nature that are built mostly out of sugar.
We're made out of sugar.
No, not as much. Just certain things. There's lots of sugar in you, but it's not the main building piece of you. like it is in say a bug or a tree.
It
Yeah.
would be like any sugar afterwards, you're all
Like sugar is
fresh.
Hold that, we'll get to that in a minute. I'm not quite ready for that just yet. Yeah. I've never heard that. Surely not, but I don't know. Never heard that. I don't know.
I don't eat.
But, you know, in a lot of places in the world, bugs are part of people's diet. Now we think it's gross here in the United States. There are lots of people in the world that eat bugs, and it turns out that eating bugs is actually probably good for you. I'm not saying you ought to go do it, but what I'm saying is that they have lots of carbohydrates, they have proteins in them. They probably are actually not a bad food source. They're anybody ever watch the Shark Tank show on TV? Shark Tank?
Yeah, well, like Shark Week.
All right, no. Shark Tank is this show where there are people that's trying to start up businesses and they're trying to get people to invest in their businesses. Anyway, here, a few weeks ago, I was watching Shark Tank, and this guy came out and he owns like a cricket farm, growing crickets, and he's making flour out of the crickets and selling it to people to make bread and stuff out of. And apparently, this flour that he's making has more protein and more nutrients in it than flour made from like wheat. And apparently, it tastes pretty good. They had cooked up some kind of bread or biscuits or something with it, and they fed them to the Shark Tank people, and they gave him money. They invested in his company. Apparently, he's making a lot of money from cricket flour, which is kind of weird. Yeah.
How come
Samantha's got the floor again.
I ate scorpion one day? How come it didn't make me sick?
I think the scorpion, I think, is only going to hurt you if it injects that into your bloodstream. So.
I mean, it was at the store.
They'd already removed this thing.
Yeah, well, how did that still not make me sick?
Well, the
That's like the nail part of the customer.
poison is concentrated near that stinger, so
I
you
mean,
gotta eat that part.
like, don't you still have to eat the bones too?
No, they don't have bones.
They don't have bones? Oh, thank God.
Bugs don't have bones.
Okay.
Yes.
Does that mean somebody can like make a churro, like feed somebody and be like, you're eating crickets?
Yeah.
That's
Oh.
All right, back to what I'm saying. Focus, guys. Sugars come in lots of varieties. There are simple ones, and there are more complex ones.
Yes. That's for me.
Yeah, for later. All right. Anyway, the most simple sugars have kind of a complicated looking name, but it's not that bad. Monosaccharide. These are simple sugars. Monosaccharides.
I can't say that.
Just listen. Mono means what? One. And saccharide just means sugar. One sugar. Simple sugar. And there's lots of monosaccharides you've heard of before. Glucose is the most famous one. Glucose is the sugar that gets made during what process? Photosynthesis. It's the basis of all food on Earth. It's where it comes from. It's the sugar that plants take sun energy and use it to make glucose. Anybody know the formula for glucose, like the chemical formula for it?
I used to know this middle last year.
C what? C6? No? H12O6. That chemical is the basis for all of life, really. It's the main fuel for all living things. Now, we're going to skip some of this stuff in the middle, but that's the most basic monosaccharide, simple sugar.
What is that other equation on the side? The C and H2.
All right, that just means that for every one sugar, for every one carbon rather, there's 2 hydrogens and 1 oxygen. So it's a ratio, 1 to 2 to 1. If you put 2 monosaccharides together, if you bond them together, like 2 glucoses or something, you get a disaccharide. That just means 2 sugars, right? There's some of those you've heard of before. I'm just going to talk about 2 of them. Sucrose. Sucrose is better known to you guys as what? What's the sugar you go and you buy in the store, in the big bags? It's called table sugar. Okay? It's what your mom probably uses to make pies and cakes and stuff out of. That's sucrose. Hold that thought. Where does that come from? The sugar that they're selling you in the grocery store, where do they get that from? They most time get it from sugar cane. So, the sugar cane plant, the sugar cane plant makes the glucose, or one of these other simple sugars, and it combines two of those together to make a slightly bigger sugar, sucrose. Another disaccharide that you probably heard of before. Hey, what's up? No, I don't have her. Another simple sugar or disaccharide you probably heard before is lactose. Where's lactose at?
Milk.
It's in milk. Milk sugar. But again, milk sugar is just two of these simple ones stuck together. Some of you, I would imagine, probably can't drink milk. Anybody lactose intolerant? You are? No. You're not? All right, if you're lactose intolerant, and let's say you drink milk, you're lactose intolerant, you drink it anyway. What lactose intolerant means is you can't digest it the right way, right? So it goes through your body, and it gets down to your intestines, like your large intestine. What lives inside your large intestine?
Bacteria.
Bacteria. Well, that sugar has come through you undigested. It gets down to your large intestine.
Yeah.
Those bacteria start eating it. And when they eat it, they start giving off lots of gas. And your large intestine blows up like a balloon, essentially. And you start having diarrhea and vomiting and pains, and it's not good. Okay? So if you're lactose intolerant, there's two solutions. One is avoid milk products. I'll get you just a second. The other is they sell this stuff in stores that's actually an enzyme that if you take it by mouth, you can start digesting lactose. You can buy the enzyme, essentially, that you're missing. Take it by powder, and then you can eat your ice cream or drink your milkshake or whatever you want to do. It'll be okay. Go ahead.
Is that the same for cheese too, if you like lactose intolerant?
Yep, because cheese is essentially fermented milk. Same thing. All right, let's go a little bit further with this. The more complicated sugars are called polysaccharides. That means many sugars, right? A polysaccharide is a sugar that's made of lots of little sugars connected together. And the one of these that you need to know a lot about, and I'll answer the question that Logan had as we're talking about this, is starch. Starch is made from lots of glucose molecules connected up together. What makes starch? Where do we get starch from?
Grain potatoes.
Plants, okay? Why would a plant make starch?
Isn't it their like heat source or something?
It's the way they store energy that they want to use a long time from now. Okay, it's their long-term energy storage. It's like kind of like almost like plant fat. You know, we store energy as fat if we want to use it a long time from now. They store it as starch. Do I know?
So that's what it is.
Yep. Potatoes, corn, rice, grains like wheat are mostly starch. Listen, please. Now, the nice thing about starch is that it's pretty easy for us to digest. And that's why it's the main thing that we eat. Up to like 70% of the human diet is starches, complex carbohydrates. And that's a good thing in most cases. Let's address the question Logan had a minute ago. Sometimes, let's say this is a graph of energy against time. Let's say that you're going to go out, you're going to play in the football game tonight, and the coach is not very scientific. I'm not saying our coach doesn't know anything about science, but I'm saying you got a typical coach. He doesn't know much about science. And he hears that, football players need a lot of energy before they play. So he's watching TV and he notices on the candy bar commercial the number of calories in like a Milky Way. And it's crazy. Crazy amount of calories in a Milky Way. So he says, man, Milky Ways have a lot of energy. My football players need a lot of energy. So our pregame meal tonight is going to be 5 Milky Ways and 2 Mountain Dews. That's That's our pregame meal. So, now here's what happens. The Milky Ways and the Mountain Dews have simple sugars in them, like monosaccharides or disaccharides, which means they are already ready for you to do what to? Burn them. Cell respiration. So as soon as, right after you drink that Mountain Dew and you eat that Milky Way, your energy level is going to go through the roof. It's going to spike. But you're going to bounce off the walls for a little while, right? Maybe the first quarter you're bouncing off the walls. But that just as quickly as that fire flamed, it also does what? It goes out and you crash. So your energy levels may even drop below where they started, and you're in that funk where you feel like you can't even like move, right?
It's like throwing napkins in fire.
Yeah, it's like throwing a tissue in a fire. It flames and then it's gone. Okay, that's sort of what happens here. What should the coach feed you if he's going to give you a proper pregame meal? Something starchy, okay? Like pasta, bread, potatoes, rice. Because here's what happens. Listen to me, please. Remember that the polysaccharides, like starch, are long chains of simple sugar. So let's say this is starch. But instead of having 3 of these markers hooked together, it'd be like hundreds of them hooked together. This goes into your body. What's your body got to do before it can burn it? It's got to break these off. And it breaks them off like one at a time. So you get a little bit of energy, but this is still there. So what happens if you eat starches is that your energy levels go up a little bit, and then what happens? And then they pretty much stay up for a long, long time because the body's got to break off all these little sugars and then burn them so that it lasts a long time. That's why when you eat like a pre-game kind of meal, starchy stuff. And you might want to get some protein in there too, like some steak, but mostly starchy stuff. Yeah.
Could they eat a bunch of Milky Ways and this pasta stuff, or
Even then, when you put all that sugar in your body, you still get that down thing. So you don't want to eat something really sugary before the game. No. All right, those are carbohydrates. They are your body's sources for quick energy, and they're also used to build things like a tree. Let's talk about one more polysaccharide for a second. There's this polysaccharide called cellulose. I'll get you in a second. Cellulose, just like starch, cellulose is made of lots of glucoses connected together. So why aren't they the same thing? They're both made out of chains of glucoses. Why are starch and cellulose different things? They're hooked together in different ways. They got a different shape. Starch is pretty easy for us to digest. Cellulose, on the other hand, is hooked together in a way that's almost impossible for us to digest. It's the stuff that the cell walls of plants are made out of. It's the stuff that wood's made out of. Cellulose. It's really strong and really hard to what? Break down, digest. Lettuce, for example, is mostly made out of cellulose. When you eat lettuce, how much energy do you get out of that? You actually get negative calories in most cases. Now, what does that mean? Negative calories. Yeah, it means you burn more calories trying to chew it and push it through your body than you get out of it.
isn't that a good thing?
Well, if you're trying to lose weight, it's a good thing. But let's say you're on a deserted island and the only food there is lettuce, you're going to starve to death. You're going to starve to death. Because you're not really getting any useful calories from it. Cellulose, on a lot of commercials on TV, you'll hear them talk about fiber, right? Fiber in your diet. Cellulose is fiber. What that means is it's something you eat, but you can't really digest it, so you put it in and it comes out the other side, pretty much unchanged. Why are they talking about all the time you need your fiber? You gotta have something to push stuff through you, right?
What about second one?
When you eat what? Same kind of thing, that shell, you can't really digest very well around it, but it's kind of the same kind of thing. But here's the thing. Cellulose is like fiber. It's like a natural laxative. And that's a good thing. You need it. It helps you stay regular. You know where I'm going. But those are carbohydrates. The next category we're going to mention are lipids. Tell you this will help you remember this. I had this friend in high school. I had some nerdy friends in high school. And we had this friend, we call him Lipid. Okay?
Lipid.
Alright, that was his nickname, Lipid. He was a little on the heavy side. Because what are lipids? They're fats, oils, and waxes. So that was his name. He was Lipid. Anyway, lipids. Like we said before, are fats, oils, and waxes. We're mostly going to concentrate on the fat part here for a minute. In your body, what are the main uses of lipids? Store energy for the long term. Store energy that you don't need right now. You're not going to need it in a few minutes. You might need it a week or two from now. But store energy for the long term. All right, what are some other uses of lipids? Other than just storing energy. Padding. Your organs have a small layer of fat around to pad them, like when you take a hit.
So you can't burn weight.
Underneath your skin, right under your skin, no matter how skinny you are, there's a little layer of fat. What's that there for?
Protection.
It's to insulate you. To help you keep your body temperature up. Okay? Here's kind of something scary. Yeah, true. But here's something else. Kind of scary. You guys know what anorexia is, right?
Yeah.
Girls who pretty much stop eating normally, they may make themselves throw up, they start losing crazy amounts of weight. Hold it for just a second. So let's say you have a girl who's anorexic, and she's been anorexic for a long, long time. There's pretty much no body fat left, right? When you stop eating, your body starts to burn your body fat. So these anorexics, sometimes, if it's really extreme, they burn the fat that's normally under their skin. So they start having a hard time doing what?
Moving.
You know, when we say that fat right under your skin was for? Keeping your body temperature up. So they start having a hard time controlling their body temperature. That's bad, right? So what does their body do to keep them alive? Yeah, but in addition, this is kind of gross. In addition, they grow this like fine coat of, for lack of a better word, fur. They grow these little white, soft hairs that act almost like a coat of fur. And that's to keep their body temperature up. So, you know, if you're ever tempted, you ladies it's almost always a girl issue, right? Anorexia is. It's not always, but usually. If you're ever tempted to do that, to lose this crazy amount of weight, I mean, being skinny might look good, but having a coat of fur probably doesn't, okay? Don't go there, okay? You don't want a coat of fur. Regardless. So lipids are fats, oils, and waxes. Their main role in biology is to store energy for the long term, but they're also good for padding. They're good for helping to insulate your body. For example, like a big seal, a big whale, they're pretty much just a big hunk of fat, right? Because most of the time, where do they live? Where in the water? Places where it's cold, the water's cold. To keep their body temperature up, they have to have a lot of fat. You know, how many of you watched Shark Week this past week or so? Sharks, that's their favorite food, right? Seals, dolphins, small whales. That's their best. They do when they catch them. That's their favorite food. And the reason they like it so much is it's loaded with fat. If you're a shark and you eat a big seal, what did you just get? What's the purpose of fat? To store lots and lots of what? Calories, energy. So if you're a shark, you want to eat something that's really fat, right? Most of the time, when a shark bites a person, what happens? Most of the time, it bites them. It says you don't taste very good, and it spits you out. Okay? Because your average person's fat content is way less than the seals or whales or dolphins. Okay? So the shark takes a bite out of a person, and there's not much fat there. It doesn't want to eat that person. It's not worth its time. It spits it out. It wants to eat something that it gets crazy amounts of calories from, which is like a seal or a whale. Yeah.
You're saying like if a really big fat guy really like in the water, it probably eats that guy.
Maybe. Maybe.
Sharks that eat people, it's because they look like something in the water.
Right, because they're on the surfboard or something and they're sticking out and like you got flippers. Sharks typically are not hunting people to eat them. Now there have been a couple of cases where sharks have kind of went rogue and started eating people as part of their diet. That's very unusual. Jaws, the movie, was actually based loosely on something that happened up around Massachusetts. But very loosely. Not all that stuff is true, not all of it really happened.
Shark called submarine or something like that.
I think that's fake. You know, something that I don't like about Discovery Channel the last couple of years is they started putting fake stuff on there. There was a show a year or so ago about mermaids. And I was sitting here watching the whole show, and I thought maybe they had found something new that nobody knew about. I didn't really think it was mermaids. But I was watching the show, and eventually, when it was over, I thought, there's no way that's true. So I got online, and I Googled it, and it's just fiction. It was all lies. And there were two shows during Shark Week this year that were complete fakes. One of them was that one you're talking about. It's completely untrue. And there's another one about this big megalodon shark, this huge shark that's way bigger than a great white. Completely untrue. Completely made up. You know, that's fine if they want to show stuff that's made up. But they need to say that this is, because it's a science channel. But they didn't do that on any of those shows. They didn't say this is fiction. They played it as if it was real.
And they do say it 3 seconds in text.
Yeah, it may be in a little bitty piece of text.
All these events are fiction-based.
Right. But it just flashes by and you don't notice it. So I'm not a big fan of that. One other thing I'll say here, and this is something you want to hear just for your own good. You hear about saturated and unsaturated fats, right? Saturated and unsaturated fats. Which one is worse for you?
Saturated.
Unsaturated.
I heard both. Which one's worse for you? Saturated?
Saturated, right?
Unsaturated.
Unsaturated.
Saturated. Okay? Saturated fats mostly come from where in your diet? Meat. Mostly come from meat, like not chicken. Mostly come from beef or pork. Beef or pork. And here's the thing. Saturated fats at room temperature usually look like what? They're like solid, like lard, for example. You guys seen lard?
Yeah.
Okay? Solid fat. When it gets into your body, it sometimes will re-solidify, particularly in places around your heart, right? And it can clog up your arteries. It can cause you to have a heart attack. Unsaturated fats, if you get way too much of those are bad for you too, but they're not as likely to cause the heart problems that the saturated fats do. So animal fats, saturated fats, are not very good for you. The unsaturated fats are better for you. Chicken doesn't have much saturated fat, neither does fish. But beef and pork do. All right, so let's try to talk about one more category at least here. Let's talk about proteins. We've already talked about some, but let's try to finish them up. Proteins are probably the most important chemicals in your body. We said that the proteins you have in your body are controlled by what? What controls the proteins you have in your body? Your DNA. It's the purpose of your DNA. Code for your proteins. Proteins are made out of 4 main elements. That carbon is always going to be there. Hydrogen, oxygen, and they also have some nitrogen, sometimes some sulfur. If I asked you for the uses of proteins in your body, what would be the best answer? everything, okay? Proteins make up your muscles. They make up your hair. They make up part of your bones. Pretty much every part of your body, if you take out the water, is mostly protein. But by far the most important proteins in your body are these little things called enzymes. I got it. And we talked about enzymes already. Thank you. It's for you for later. Enzymes are proteins in your body that do what? What do enzymes do for you? Yeah. We're gonna say that enzymes are catalysts. We talked about them a little bit already. What did it mean to be a catalyst?
To speed something up.
Not necessarily to speed it up, but to cause it to get started in the first place. Well, not so much. Here's what enzymes do. A lot. Do you want me to share that with everybody? Or? Let's just pay attention. All right. Enzymes are catalysts. They make reactions happen in your body. Reactions that normally wouldn't happen under normal conditions. For example, you put some starch in your mouth. You hold it there for a little while. Starch at first, what does it taste like? It's just pure starch.
Salty a little bit.
No, pure starch. Let's say just a grain of white rice in your mouth. It doesn't taste like really anything, right? Unless you add some salt or something. It's just starch. But if you hold it there for a while, what starts happening? It starts getting sweet. Because you have enzymes in your saliva that take that starch, which remember is a long chain of sugars, and it breaks them apart. And a simple sugar like glucose, what does it taste like? It tastes nice and sweet. That's glucose does. So in your mouth, that starch is getting broken down into things that taste nice and sweet. That's what enzymes do. But get this through your head as well. Most people hear the word enzyme, and they think break down, right? That's what somebody said over here a minute ago. Enzymes break things down. There are just as many enzymes that cause this to happen as there are that cause that to happen. Enzymes make reactions happen. Whether they're putting together reactions or taking apart reactions, they make things happen in your body. Your DNA's main job is to code for enzymes. And enzymes then make you work. They make reactions in you happen. Proteins are made out of these chemicals called amino acids. You guys have heard of those before, right? Anybody? A lot of bodybuilders. Do we have any football players in here? All right. Well, a lot of guys when they get on weights, they'll go to a place like GNC. Yeah, I can tell you a bit on them hard, but I'm sorry, Daddy. When you go to a place like GNC, they sell this powdered amino acid gunk. Okay? It's not. This is different than creatine. But you buy this powdered amino acid stuff and you pour it into like a drink and you make shakes. Okay? You're drinking like a shake of amino acids. Why would you want to do that if you're lifting weights?
Make water weight that's harder than muscle.
Well, here's the thing. What your muscles are mostly made out of what? Proteins. And what are the building blocks of proteins? Amino acids. So if you're going to make new muscle, you have to have the pieces to make it out of. And that's why you would take all these amino acids, is to give your body the pieces to build new muscles. Yeah. Creatine is an energy source. It's supposed to put more energy in your muscles. It's not about building muscle. It's about putting energy in there to make them grow.
You lose fat if you don't work out.
Oh yeah, it's got a lot of calories in it. Yeah. The amino acids. I'm assuming with the amino acids they're using some protein source. I don't know if they're using meat or if they're artificially extracting it from something. I'm not sure. I'm not sure how they make the protein shakes. But let's look at this for a second. Well, let's just do this for right now. Proteins are made of amino acids. There are 20 different amino acids in nature. So all the proteins in your body are made out of only 20 different things. If you eat a nice big steak, what do you get? You get all 20 amino acids. you can make any protein you need to make. If you eat a big slab of fish or chicken or pork, you get all those amino acids. But if you're a vegetarian, it becomes a little more tricky. Plants have some amino acids in them, but most plants don't have all amino acids. So if you're a vegetarian, you don't want to be uneducated about your diet. You have to eat certain combinations of vegetables to get what you need, okay? Because you don't get all the amino acids from all the plants. You have to eat certain combinations to get them all. You got to be kind of smart to be a vegetarian because you have to be careful with your diet. Yeah.
Okay, well, you have to be smart to know to be vegetarian. I don't understand that.
I'm just saying you have to monitor your diet and only eat certain things.
Well, I know this. I don't eat meat, but
Oh.
yeah. Like, how do you have to be smart?
Well, I'm just saying you have to be smart about what you eat. I'm not saying you have to be Einstein or something. I'm just saying you have to be way more careful. You have to plan your meals more. You can, if you eat a hamburger, you get all your amino acids. Vegetarians aren't doing that. All right, we have one more little group we got to talk about. Hold on, we'll come back to that. One more group we got to talk about, and that other group is nucleic acids. Join me, please. Nucleic acids are hugely important chemicals in your body. Their main functions are to store and pass on genetic information or to store energy. Two different things that they do. Store and pass on genetic information, store energy. There are three nucleic acids I want you to know about. We'll let the bell finish and then we'll go. Did you get through with those stuff?
No, I got most of it.
All right, here's the deal. The three nucleic acids that I want you to know about are DNA. Hey, Brandon, that's not our bell. We got 15 more minutes. The three nucleic acids you need to know about are DNA, RNA, and ATP. If it's an acronym in biology, it's probably a nucleic acid.
What's the difference between DNA and RNA?
All right, I'm getting there. I'm getting there. Hold that thought for a second. But DNA and RNA, they're both about storing genetic information, right? Coding for proteins, controlling traits, storing genetic information. That's DNA and RNA. ATP, on the other hand, is about storing what? Energy and transferring it to other places. We said polysaccharides, what are their building blocks? Polysaccharides like starch are made out of monosaccharides. Proteins are these big molecules made out of. Proteins are made out of what were we just talking about? What are the bodybuilders drinking? Amino acids. Nucleic acids are big molecules made out of small pieces called nucleotides. And let's look at a picture here of how this might work. Here's what a nucleotide looks like. A nucleotide has a sugar in the middle, so it has a carbohydrate in it, but it also has a nitrogen base. Now, I know somewhere in biology, in middle school, you talked about DNA and you talked about A and T and G and C, right?
Oh, yes.
Okay? A and T and G and C. The bases, those are the nitrogen bases that are part of these nucleotides. You probably talked about phosphate groups too. But those three things together make up a nucleotide, a building block of a nucleic acid. And we're going to briefly talk about those three amino acids, or those three nucleic acids, DNA, RNA, and ATP.
Okay. How come, because if you eat just vegetables, and you can't lose much weight without meat being here. Because without meat, my mom said without meat, I'd die eventually.
That's not true. As long as you eat the right combinations of vegetables, that's not true.
Well, I just eat vegetables. I
You need to.
I don't understand this.
Yeah. You have to eat certain kinds of vegetables in combination to get all the things you need.
Well,
Eats vegetables.
You need to read a little bit about being a vegetarian before you really are a true vegetarian.
No, I will.
You should read a little
But I
bit.
don't like.
Anyway, back to what I'm saying. Back on track here. DNA, you guys should all know it's deoxyribonucleic acid. That's what it means. We've already said in here over and over again that DNA's job is just that. It codes for proteins. It tells your body, hey, I need this protein, and here's how you put it together. You might think of DNA like the blueprints for a house, where your body is the house. Okay? It's the directions for putting you together. That's what DNA is. We know that your DNA is stored in the nucleus of your cells, and that it has that double helix shape. It's like a spiral staircase. And I'm not going to say anything else about it for right now. Those are the things you need to know about DNA. Okay? It's a nucleic acid. It's deoxyribonucleic acid. Its job is to code for proteins. Think of it like the blueprint for building your house. Not for right now. We'll do that later. It's stored in the nucleus. It's got a double helix shape. All right, and then let's finish up. Just listen for a minute. I'll go back in just a minute. I need everybody to focus. This is what DNA looks like. That's what a double helix means. It's a 3D spiral, essentially. All right, so I'll leave that there for a minute. What we've got to do before we take that test on Tuesday, we still need to talk about RNA and ATP. We got to talk a little bit about enzymes, but on Monday, we will finish those up to begin with. That'll take all of maybe 10 minutes or so. We're going to do a little bingo game on Monday, okay? To help get ready for your test. I'll give you like a blank bingo sheet. Just listen. Listen to what I'm saying. I'll give you a little blank sheet. It's got, I don't know, bingo's what, 5? So it'll be like a 5x5 board of squares. And then I'll write a list of words up on the board. Words that you need to know the meanings of for the test. It's going to be on Tuesday. You will pick 25 of those words. You will write them one word per box on your bingo sheet. And then I'll start asking questions. And if you think you have the answer on your bingo sheet, you'll mark it. And then we'll do that 2 or 3 times through to help you get ready for the test on Monday. Yeah.
My mom's downstairs, let's say we all have it.
Yeah, they should call and bring a note up. Yeah. Yes, I'm gonna get it. All right. Let me turn off the recording here first. Just hold up.